Fact 1. The term artificial intelligence originated in 1956. This occurred at a summer school in Dartmouth, where John McCarthy proposed the name for the field, aiming to enable machines to learn any aspect of intelligence. In practice, things began slightly earlier. In 1950, Alan Turing proposed a test to determine if a machine's responses were indistinguishable from human ones. In 1956, Newell and Simon demonstrated the logic theorist program, which proved theorems. And in 1958, Frank Rosenblatt introduced the perceptron, a simple, trainable recognition model. This was followed by periods of advancements and AI winters. These involved excessive promises and funding cuts in the 1970s and late 1980s, alternating with new breakthroughs. This cyclical nature is a crucial part of the history. Expectations overheat, then methods are refined, data and computation catch up to ambitions, and the wave returns stronger. A modern neural network is a cascade of linear transformations and nonlinearities, where millions and billions of weight numbers are slightly adjusted for the task. Training proceeds as follows. The network makes a prediction. A loss function measures the error. The backpropagation algorithm calculates how exactly to change each weight, and stochastic gradient descent takes a tiny step towards a better solution. Activations like ReLU sped up deep layer training. Regularization, e.g. dropout, and normalization stabilized gradients. Mini-batches and optimizers like Atom added flexibility. Models are trained on GPUs and specialized accelerators, TPUs and their equivalents, where thousands of cores multiply matrices in parallel. An important detail: training and inference are different modes. The former is greedy with data and energy. The latter is optimized for speed and cost. The third fact is that the combination of transformer architecture and scaling became a turning point. In 2017, the concept of attention was introduced, a mechanism that allows a model to weigh the connections between any parts of the input without resorting to recursion or convolutions. This significantly simplified parallelization and opened the door to giant models. Subsequently, empirical scaling laws came into play. As parameters, data, and computational steps increase, the validation error decreases according to a power law. Not infinitely, but predictably, as long as quality data is available. This led to a race: more tokens, more context, fine-tuning for domains, and chain-of-thought training. Claims about the emergent abilities of large models remain a subject of debate. Some effects are explained by the smooth quality curve and task thresholds, but the fact itself remains. Scale will continue to yield significant returns for a long time. Fourth fact: large language models do not know facts in a strict sense. They guess the next text fragment based on statistics from vast corpora. This leads to the hallucination phenomenon: convincing but incorrect answers when the context is ambiguous or data is insufficient. This is not lying, but a consequence of the probabilistic nature of generation and the lack of direct access to sources at the time of the answer. To reduce the risk, methods like fine-tuning with human feedback, RLHF, connecting external search and knowledge bases, retrieval-augmented generation, strict format constraints, tool-based validation, and chain-of-thought verification, where the model explains steps that are then checked, are helpful. However, there is no complete guarantee. The broader the topic and the newer the fact, the more verification and careful phrasing, such as "according to estimates" or "as of," are needed. Fifth fact: AI ethics and regulation have become as important as model accuracy. Systems inherit biases from data, gender, racial, cultural, and without alignment measures, they will amplify them in decisions. In response, audit practices, dataset and model cards describing limitations, metrics, and risks have emerged. Law is also catching up with technology. The EU has approved a comprehensive AI Act with risk grading from prohibited, e.g. manipulative biometrics, to high risk, medical, financial, infrastructure applications with strict data governance and transparency requirements. Sharp questions remain: the permissibility of training on copyrighted corpora, personal data protection, and liability for damages from automated decisions. A conservative practice is human-in-the-loop, logging, and verifiability. Fact 6. In AI, not only architecture but also data composition is crucial. Large models absorb the world from a mix of web pages, books, code, dialogues, images, and sound, and the quality of this mix is critical. Noisy, toxic, or legally questionable sources introduce biases and errors. The data pipeline is a separate engineering discipline. Collection, considering licenses, cleaning, deduplication, language and topic filters, domain balance, and then controlling test contamination so the model doesn't see answers beforehand. Synthetic augmentations are popular. When a strong model generates instructions and analyses for training more compact ones, but this requires checks, verifying diversity and plausibility. The finishing touch is instruction fine-tuning and alignment for safe responses, where not only accuracy but also tone, boundaries, and refusal of harmful scenarios are important. Fact 7. Reinforcement learning is when an agent learns to act by receiving rewards for success. A notable example is programs that have beaten champions in Go and chess. There, agents trained in simulations, improving their strategy time and again. But the world beyond games is more complex. Rewards are vague, environments are unstable, and mistakes are costly. Therefore, safe exploration, imitation of expert trajectories, offline learning from logs, and careful reward formulation to avoid encouraging cheating are used. In real robotics, simulators and transfer to physics are critical. In recommendations, control over the groove of preferences is needed so the system doesn't narrow the user's horizons. And also, RL is often combined with world models or large language models so that planning and explainability go hand in hand. Eighth fact: computer vision has evolved from handcrafted features to deep networks. A breakthrough in image recognition occurred when convolutional architectures drastically reduced error rates in large-scale competitions. Subsequently, residual connections were introduced, enabling the construction of very deep networks. Later, visual transformers emerged, bringing attention mechanisms into the realm of pixels. Today, a single model can simultaneously localize objects, segment scenes, estimate depth, and determine pose. However, subtleties exist. Domain shifts, for example, models trained during the day struggle to operate at night, rare cases, and sensor drifts undermine confidence. Therefore, benchmarks focusing on the tails of distributions, synthetic data augmentation, and tests for robustness against weather, glare, and compression artifacts are important. In medicine, a second loop is added. A doctor confirms the findings, and the system records confidence levels and explainable features. Ninth fact: prompt engineering has become a craft. How you formulate the task determines how the model will respond. System instructions set the style and boundaries. Few-shot examples demonstrate a solution pattern, and strict formats, like requiring JSON with a schema, reduce ambiguity. Connecting tools, calculator, search, databases, turns the model into an orchestrator that decides when to think and when to ask an external service. A vulnerability is prompt injection. Malicious insertions in data or on web pages try to rewrite the rules. Protection is built on context isolation, filters, source verification, and a least privilege policy for tools. There are also false explanations. If you ask to show reasoning, you won't necessarily get the truth. So for critical tasks, hidden chains and external verification of steps are used. 10th fact: the AI economy is a fight for efficiency. Training giant models requires months of computation and careful budget planning. How many parameters, how much data, how to distribute training across devices, and how to reduce downtime. At the deployment stage, optimizations are important. quantizing weights to 8 or 4 bits without quality loss on target tasks, pruning insignificant connections, and distilling knowledge into more compact networks. Plus, serving engineering, batching requests, caching attention keys, sharding across nodes, and prioritizing traffic. Data centers consider not only money but also water and electricity, aiming to reduce their carbon footprint and overheating. On the user side, hybrid schemes win. Part of the inference on the device, part in the cloud. Faster, more private, and cheaper with proper orchestration. Fact 11. Multimodal models combine text, images, sound, and video into a single representation to understand a scene and talk about it in human language. The basic technique is contrastive learning. A picture-caption pair is brought closer in a shared feature space, while mismatched pairs are pushed apart. Visual tokens are obtained by dividing a frame into patches, sound through spectrograms, and video by adding timestamps to a sequence of frames. Next, dialogues are trained on top of this, relying on pixels, answering questions about a snapshot, describing diagrams, reading interfaces step by step. This opens up accessibility, scene recognition for the visually impaired, analysis of medical images with textual justification. But errors are also characteristic. Object hallucinations, when the model confidently sees in a photo what often co-occurred in the data but is absent here. Therefore, source control and answer verification remain mandatory. Fact 12. Speech recognition has moved from gluing acoustic and language models to end-to-end architectures. CTC and RNNT were long the standard for streaming dictation. Then, transformers learned to work piecewise with low latency. The difficulty lies not only in phonemes, but also in the surrounding world: noise, accents, language mixing, proper names, jargon. For reliability, domain adaptation, personal dictionaries, and online microphone normalization are combined. The flip side is speech synthesis. Modern TTS uses neural vocoders and diffusion decoders, which convey timbre, pauses, and breathing. It's possible to change style, speed, emotions, and sometimes even clone a voice from a few seconds of sample. This is powerful but sensitive. It introduces risks of biometric spoofing and fraud, hence the growing demand for anti-spoofing, watermarks, and explicit consent policies for voice usage. Fact 13. Image and video generation relies on diffusion processes. The model learns to remove added noise step by step, turning randomness into a meaningful picture. This is often done in a latent space. The image is first compressed by an autoencoder to speed up computations, and then diffusion works with compact representations. Control is achieved through natural language prompts, in-painting masks, depth maps, pose information, or sketches. There is also a classifier-free guidance technique that allows controlling how strongly the output follows the prompt. Video adds the problem of consistency between frames. Optical flow, keyframes, and motion anchors are used. And for 3D, radiance fields and Gaussian splats are employed to preserve geometry. The ethical part involves detecting and marking synthetic content, protecting individuals, prohibiting harmful scenarios, and respecting copyright on training datasets. Fact 14. AI explainability is a set of methods, each highlighting a part of the mechanics but not providing a complete X-ray of the whole. Saliency maps show which pixels or words most strongly influence the answer. Integrated gradients assess feature contributions. Lime and Shap build local linear approximations around a specific example. In transformers, attention heads and activation pathways are explored, sometimes identifying typical roles like template copying, bracket matching, or tracking long-range dependencies. There's also a mechanistic line of research: feature visualization, linear probes, and careful experiments to disable chains. However, an important warning: attention maps do not equal causality, and a nice graph is not a guarantee of the conclusion's correctness. Practice requires benchmarks for explainability, replication of results, and comparison of interpretations with changes in the model's actual behavior. 15th fact: AI evaluation is becoming a discipline in itself. Classic classification and translation tests have been replaced by multi-industry exams, logical problems, programming, mathematics, and step-by-step solutions with output verification. This process leads to leakage. Models might have seen similar questions during training, making test purity, secret datasets, and regular task rotation important. For conversational systems, metrics for factuality, toxicity, resilience to provocations, and prompt injections are added. For code generation, test execution is used. For images, blind human comparison based on composition and text adherence criteria is applied. Increasingly, automated judges, powerful models that compare weaker models' answers, are used, but they are also calibrated against human evaluations. Good practice involves multi-aspect checks: accuracy, safety, timeliness, and cost under real-world load. Fact 16. The neurosymbolic approach attempts to combine the power of statistical learning with the precision of logical rules. Broadly speaking, a neural network can recognize and generalize, while the symbolic part checks by the letter of the law, whether the answers comply with tabular constraints, ontologies, business rules, or regulations. This can manifest as calling a constraint solver after generating a plan, embedding many languages, DSL, for formulas, or querying a knowledge graph where relationships between entities are explicitly defined. The advantage is controllability. It's possible not only to explain why a solution is permissible, but also to guarantee prohibitions. Example, a patient with an allergy will not receive medication from a forbidden list. The drawback is the fragility of the interface. Overly strict rules undermine flexibility, while overly lenient ones lose guarantees. Therefore, architectures are built in layers: recognition, then verification, then adjustment with feedback. Fact 17. Agent systems based on large language models aim to transform a model from a responder into an executor of multi-step tasks. An agent maintains a goal, plans steps, invokes tools, search, code, tables, APIs, reads results, and adjusts its course. A multi-agent setup divides roles: a planner, an executor, a reviewer. Another scheme involves a single agent with a reasoning loop and short-term memory of previous steps, reinforced by a long-term vector store. This is useful for integrations, from semi-closed RPA processes to document analysis. However, risks exist: infinite loops, overconfidence, getting stuck on a wrong hypothesis, and vulnerability to external prompts from data. Practice implements guardrails, limits on steps and budget, code sandboxes, API whitelists, critical action verification, logging, and offline scenario evaluations before production launch. 18th fact: AI privacy and security are not just about content filters. There are membership inference attacks that try to determine if a specific example was included in the training data. There is model inversion, an attempt to reconstruct original records from model responses, and data poisoning, where an attacker injects poison into a dataset and alters the system's behavior. In federated learning, gradients themselves pose a leakage risk, so secure aggregation and differential privacy are used. Differential privacy adds noise and formally leaks leaks, albeit at the cost of accuracy. For deployed systems, prompt filters, tool isolation, and protection against secret extraction from connected sources are important. Secure practice includes red teaming, personal data leakage tests, anomaly monitoring, and a policy of minimum necessary rights for each integration. 19th fact: AI is increasingly working at the intersection of science and medicine. Models help predict protein structures and molecule interactions, generate drug candidates, rank them by properties, and suggest experiments. The hypothesis-synthesis measurement cycle is accelerated through active learning and automated robots in digital labs. In clinics, algorithms support image reading, highlight suspicious areas, suggest probable diagnoses and risks, and aid in triage in overloaded departments. But the key is validation. The transfer from retrospective data to real patients often breaks down. And without clinical trials, oversight, and accounting for gender, age, and ethnic group biases, decisions can be harmful. The ethical norm remains the same: human-in-the-loop, transparent application criteria, and tracking impact on treatment outcomes. Fact 20. AI sustainability is about electricity, water, carbon footprint, and hardware. Training large models requires massive matrix operations. Data centers strive for cooling efficiency and low PUE, and companies move tasks to locations with more green generation. Algorithmic measures include quantization and pruning, reusing trained components, distilling knowledge into smaller models, and adapting via low-rank layers instead of full retraining. For inference, on-device processing helps by performing some computations locally, reducing latency and network traffic. In hardware, specialized accelerators are growing, and alternatives like spiking and analog approaches are being researched. Currently experimental but promising for energy efficiency. Responsible practice involves accounting for a project's carbon budget, scheduling runs based on renewable energy availability, and thoughtful hardware upgrades to reduce e-waste. Fact 21. Embeddings are a method of transforming a word, phrase, code, or an entire page into a point in a multi-dimensional space where proximity corresponds to semantic closeness. With such coordinates, semantic search becomes possible. We compare cosine distances or dot products and find neighbors by meaning, not by letters. To make the search fast, approximate indexes are built. HNSW graphs, IVF with product quantization, and documents are cut into chunks with overlap so that a query does not miss the relevant paragraph. Pitfalls are real. In high dimensions, hubness arises. Universal magnet fragments. Vectors can be anisotropic and require normalization. Universal embeddings do not always match domain-specific vocabulary. Practice adds query re-encoding, a cross-encoder for re-ranking, metadata storage, and strict quality checks using recall at K and MRR on real tasks. Fact 22nd. Retrieval Augmented Generation, RAG, acts as an external memory. Before generating a response, the system retrieved relevant pieces from an index and places them into the context, enabling the model to rely on fresh sources. A good RAG involves not only embeddings, but also a precise pipeline. This pipeline includes document normalization and tagging, strategies for chunking and titling, filtering by dates and languages, re-ranking, deduplication, and marking citations and confidence levels. A significant threat is prompt injection from the retrieved text. Overheard instructions can attempt to rewrite the rules, so it's advisable to use sandboxes for tools, whitelists for actions, and escape sequences for insertions. For robustness, caches are added. Self-consistency is achieved through multiple queries. Long blocks are compressed, and a fallback to web search is implemented. Evaluation is done end-to-end, assessing factual correctness, response completeness, the proportion of information with links, and token economy under real-world load. Fact 23rd. MLOps for AI is an operational discipline where the model is just one artifact among data, code, and infrastructure. Everything is versioned: data sets, features, weights, containers. Pipelines are built as DAGs with reproducible steps. Deployment begins in shadow mode, then moves to canary deployment on a portion of traffic, followed by A/B testing with clear metrics and a rollback plan. Online monitoring tracks P95/P99 latencies, errors, costs, as well as data, distribution shifts, PSI, KL, training prod drift, and fairness across segments. Alerts are needed for drift, automatic index rebuilding, and periodic benchmark reevaluation. Feature stores and online feature stores reduce drift, while logging requests and responses creates fuel for retraining. The key is processes, security regulations, checks for toxicity and leaks, access control to sources, and regular postmortems for incidents. Fact 24th. Tokenization is an unobtrusive yet critical layer between text and the model. Instead of letters, subwords are used. Algorithms like BPE or sentence piece group frequently occurring segments to reduce word splitting. This affects everything: the cost of a phrase in tokens, the amount of context that can be included, and how the model handles morphology. Languages without spaces, such as Chinese or Japanese, are often more token compact. Conversely, languages rich in word forms, like Finnish, tend to expand. Byte-based schemes are helpful for rare characters and code, but fragment numbers and mathematical formulas, complicating computational tasks. In multilingual models, a shared vocabulary facilitates knowledge transfer but consumes slots for rare combinations. A domain-specific tokenizer for code or chemical formulas is sometimes justified. In production, it's important to fix the tokenizer version, as changing the markup can subtly break compatibility for prompts and old examples. Fact 25th. In robotics, AI moves from the screen into the physical world. Here, beyond understanding text, sensors, dynamics, and safety are crucial. Visual motor policies link images to manipulator actions, and language becomes an interface for goals, such as pick up the red mug and place it to the right of the plate. Training is built on imitation from demonstrations, further refined in simulation, and then transferred to reality through domain randomization, which adds noise, friction, and lighting variations. Tactile and force sensors help prevent breaking objects, while SLAM and 3D scenes ensure localization and trajectory planning. Strict limitations apply: real-time operation, dependency on delays, and hard limits on speed and forces when near humans. Practice relies on a safe stack: stop contours, space zoning, goal verification before grasping, logging every contact, and predictable behavior in case of lost vision or communication. Fact 26th. Vulnerability to adversarial examples is a weakness of many models. Adding barely perceptible noise to an image, found using methods like FGSM or projected gradient descent, causes a classifier to confidently see a turtle as a rifle. Worse, attacks also work in the physical world. Stickers on road signs or patterns on a t-shirt can fool detectors. Defenses exist, but none are a silver bullet. Adversarial retraining improves robustness but often reduces accuracy on clean data. Randomized smoothing provides probabilistic guarantees in a neighborhood around a point but is limited by the size of that neighborhood. Anomaly detectors catch some attacks but suffer from false alarms. A realistic strategy is multi-layered: strict input filtering, domain shift monitoring, validation against distribution tails, and operational telemetry for early failure detection. Fact 27th. Models often overestimate their confidence. Low max probabilities suggest "I am confident" even when the answer is incorrect. Calibration corrects this flaw. Simple temperature scaling on validation aligns the probability scale. Ensembles and MC dropout provide uncertainty estimates through prediction diversity. Conformal prediction goes further, returning not a single class, but a set where the true class is included with a given probability. In regression, this results in intervals. In production, such modesty is helpful. A system can abstain, ask a human, or request more data. However, calibration needs maintenance. Shifts in traffic and new model versions can subtly break it. Good practice includes regular stress tests on rare cases, monitoring expected cross-entropy risk, and implementing a selective response policy where the cost of error is explicitly compared to the cost of abstaining from prediction. Fact 28. On-device AI is about privacy, latency, and energy. Today, phones and laptops use NPUs and accelerated operators that run local models for speech recognition, photo filters, auto-completion, and even compact dialogues. To fit within thermal and energy budgets, weights are quantized to 8 4-bits. Sparsity is applied, operations are fused, attention caches and efficient blocks are utilized. Plus personalization, fine-tuning on one's own dictionary, voice, or style, without uploading raw data to the cloud. The constraints are stripped: memory, bandwidth, background tasks. This is why hybrid schemes are in demand. Part of the logic locally, part in the cloud, with smart switching when the network is poor. The front end is also important. Web GPU and mobile graphics APIs allow inference to run directly within applications, maintaining control over user data and ensuring instant interface responsiveness. Fact 29. AutoML automates the routine of searching for hyperparameters and architectures. Bayesian optimization, evolutionary strategies, and population-based learning extract quality while the engineer sleeps. And weight-sharing NAS reuses weights to evaluate many candidate networks without full retraining. The reality, however, is more complex. It's easy to overfit to a benchmark, peak at validation, or spend a budget chasing hundreds of a percent. The trend in recent years is less architecture magic and more data and adaptation. LoRa layers, domain-specific fine-tuning, and proper corpus slicing and cleaning yield greater effects for less money. A mature AutoML stack covers not only models but also pipelines, dataset versioning, automatic drift detection, index restarts, experiment cost control, and reporting with fixed protocols, ensuring that every improvement is reproducible. Fact 30. Graph neural networks learn from relationships. Nodes are entities. Edges are connections. Then comes message passing. Each node aggregates messages from neighbors and updates its representation. Variants include GCN with averaging, GraphSage with trainable aggregators, and GAT with attention to important neighbors. Applications are broad: recommendations, user, item, event, fraud detection, transaction schemes, chemistry, molecules as graphs, logistics, and knowledge. Difficulties also exist. Over-smoothing blurs distinctions in deep passes. Over-squashing compresses distant information into a narrow bottleneck. They are combated with skips, jump connections, positional features, subgraph sampling, and hierarchies. Scaling requires many batches of subgraphs and distributed storage. For explainability, important paths and motifs are highlighted, showing which connections pushed the model to a conclusion, a necessary measure in sensitive domains. Fact 31st. Self-supervision has become a quiet revolution. Models learn from free signals within the data itself, without manual labeling. In text, this involves masking tokens and reconstructing missing parts. In images, it includes contrastive tasks like grouping similar views and separating different ones, predicting augmentations, or restoring blurred patches. In audio, it's about predicting hidden representations wave to Vec 2.0, where the network guesses future spectrum segments. Such pre-training methods create universal features that are easily fine-tuned for specific tasks, thereby lowering the entry barrier for domains with a shortage of labeled data. However, there are also pitfalls: representation collapse without negative examples, cheating through augmentation artifacts, and hidden test data leakage during corpus collection. Practice involves strict deduplication, task mixing, regularization, and mandatory transfer benchmarks on independent datasets. Fact 32. Continuous learning breaks models due to catastrophic forgetting. After training a network on a new task, you suddenly lose old skills. Several classes of methods are used to combat this. Regularization methods, e.g. elastic weight consolidation, fix important weights by penalizing large shifts. Replay buffers store a small sample of past examples or their compressed prototypes. Generative replay synthesizes memories using an auxiliary model. There are approaches with separate heads attached to a common body, as well as architectures with parameter growth, progressive nets, adapters, and LoRa modules for tasks. In production, domain shift detectors are added, a canary evaluation policy for old scenarios is used, and a forgetting avoidance budget is set. If degradation exceeds a threshold, training is rolled back or data streams are mixed until stabilization. Fact 33. Causal inference aims to answer what happens if we intervene, rather than what is it associated with. The formal approach relies on directed acyclic graphs, backdoor criteria, and the do operator, allowing us to separate observation from intervention. Identifying effects requires closing the backdoor, finding instrumental variables, or building propensity score stratification. Counterfactuals go further, exploring what would have happened to the same person with a different decision. In machine learning, this aids in marketing uplift models, medical A/B tests, and explainable credit scoring policies. Limitations are notable. An incorrect causal diagram leads to false confidence, unobserved confounders distort estimates, and complex interactions demand domain knowledge. Mature practice combines causal hypotheses, simulations, and pre-registration of analytics. 34th fact. Code generation by language models has become a working tool, ranging from completing lines to creating functions based on specifications. However, code is a verifiable artifact, so the environment is built with safeguards. Mandatory unit tests, static analysis, linters, typing, execution in a sandbox with limited privileges, and an iterative repair loop where a failed test becomes a hint for correction are included. The quality of training depends on licenses and repository cleanliness. Secrets, keys, and compromised samples are removed, and copy-paste and generic solutions are filtered out. Typical failures include compilable but logically incorrect code, insecure patterns, failure to consider edge cases, and dependency on specific library versions. Therefore, in production, human code review is maintained, dependency versions are pinned, and success is measured not by synthetic benchmarks but by task completion speed and defect reduction. 35th fact. Time series forecasting extends beyond ARIMA and Prophet. Transformer architectures, Informer, Autoformer, Patch TST, learn from long-term dependencies and external features, weather, promotions, calendars, commodity prices. Modes are important. Short-term horizons for inventory management, medium-term for data center capacity, long-term for infrastructure planning. Anomaly detection is also crucial. STL and seasonal trend decomposition, Bayesian change points, QSUM, and autoencoders with reconstruction error. Key risks include leakage using future information in features, concept drift, and regime shifts, covariate shift. Practice requires rolling origin cross-validation, predictive interval construction, accounting for holidays and promotions, and causal backtesting. Interventions like price caps or lockdowns change the data generation mechanism itself. Fact 36. Human in the loop is not a slogan, but an engineering necessity where data is ambiguous. Annotation involves not just labels like cat/not cat, but instructions, examples of edge cases, rejection criteria, and a dispute resolution protocol. Quality is measured by agreement between annotators, Cohen's kappa, Krippendorf's alpha, maintained with golden tasks hidden in the stream, and performer calibration. Active learning saves budget. The model suggests most useful difficult examples for manual review to improve decision boundaries faster. In complex domains, error atlases and taxonomies of disputed cases with examples are created. Ethics and safety are also important. Anonymize personal data, filter toxic content, and protect moderators' mental health. The outcome is an iterative cycle: collect, annotate, analyze errors, refine instructions, repeat, until metrics stabilize and the distribution and production starts to drift. Fact 37th. Fairness in AI is not a single metric, but a family of incompatible goals. Demographic parity aims for equal proportions of positive decisions across groups. Equality of opportunity requires identical levels of true positives and false negatives. Calibration seeks to ensure probabilities are fair within each segment. These criteria cannot be met simultaneously when base rates differ, necessitating choices and documented trade-offs. Tools include data pre-processing, rebalancing, feature debiasing, training penalties, and post-processing of thresholds by group. However, blindness to sensitive features does not equal fairness, as proxy features can still leak through. Production systems add segment-specific monitoring, stress tests on extreme subsamples, appeal procedures, and explainable reasons for rejections. Responsible practice considers context, legal requirements, group risks, and the cost of different error types. 38th fact: knowledge distillation and adapters transform heavy models into practical ones. In the classic approach, a teacher model provides soft probabilities or hidden representations, and a student model learns to follow them, often achieving surprisingly close quality but faster and cheaper. There are subtleties. Distillation based on answers can reinforce hallucinations, so mixed data sources, validation filters, and self-correction elements are used. Adapters and LoRa add low-rank matrices to specific layers, allowing the same base to be transferred to dozens of domains without full retraining, convenient for versioning and rollback. A parallel trend is sparse mixture of experts models. A router selects a few experts per token, saving computation with a huge overall size. Load balancing, routing stability, and compatibility with attention caches during inference are important there. The result is a modular stack, a base model, a set of adapters, and a selection policy. Fact 39. Testing and observability for LLM applications necessitate new habits. Instead of a single metric, a set of scenarios is used: golden prompts with reference answers, data sets for factual accuracy, resilience to jailbreaks, external source injections, and toxic provocations. Automated evaluators assess style and schema adherence, e.g. strict JSON, but for sensitive tasks, human revision rotation is maintained. At runtime, telemetry is collected: parsing failure rates, speed, cost per token, tool call frequency, and PII flags. Guardrails are implemented: token limits, timeouts, a circuit breaker for error spikes, input-output filters, schema validation, and post-processing. Canary deployments and A/B testing by task groups prevent regressions. Incident logging with reproducible repros and lessons learned is key to maturity, ensuring prompts, tools, and policies are consistently improved. Fact 40. In education, AI has become both a calculator and a coach. Interactive tutors explain steps, adjust difficulty, generate similar problems, and provide instant feedback, especially valuable in languages and math. Text assistants help with essay planning, drafts, and argument structure, but require a clear academic integrity policy, usage notes, source citations, and a ban on passing off others' work as one's own. AI assists teachers with formative assessment, transcribing oral responses, rubrics, highlighting gaps, and offering individual recommendations. It enhances accessibility, subtitles, text-to-speech, and dyslexia adaptations. Risks include hallucinations, cultural biases, and over-reliance. Therefore, human-in-the-loop, fact-checking, and open retrieval are basic standards. Best practices involve creating transparent assignments, part with AI as a tool, part in the classroom without prompts. Fact 41. Long context is not a cure-all. Models can indeed hold tens and hundreds of tokens in their memory, but attention is distributed unevenly. The beginning and end receive priority, while the middle gets lost. This effect is called lost in the middle. Positional encodings have evolved from absolute to relative and rotary rope, and heuristics like ALIB, sliding windows, and sparse attention, where the model only looks at reference anchors, have emerged. In production, a combination wins. Meaningful segmentation in headings, extraction of relevant fragments before the answer, compression and deduplication, and then careful placement into the context with citations. Key value caches and session-based history reuse technically assist, but injection and contradiction risks grow. The golden rule is simple. Long context is an expensive resource, so it's better to find what you need first and then read everything else. Fact 42nd. Structuring responses turns a language model into a reliable system component. When JSON, SQL, or a precise function name is needed, mere please is insufficient. Decoding constraints are required. In practice, methods like context-free grammar, CFG, inference masking, masking invalid tokens, strict JSON schema adherence, and function calling are used where the model selects from a list of permissible tools and fills in their parameters. It's important to remember that zero temperature does not guarantee the absence of misplaced commas. Hence the implementation of generate, check, fix loops, stream validation, and field length limitations. A separate threat is data injection. Pseudo-JSON encountered in a document can disrupt the parser or convince the model to speak outside the brackets. Good practice includes escaping, initial schema validation, error reporting instead of free text, and parsing failure metrics as a key quality indicator. Fact 43rd. Corporate AI implementations are primarily about trust architecture. Before connecting internal documents, DLP and PII retraction are enabled. Secrets are removed and access rights are projected into the index so that issuance respects ACLs. Serving is isolated network-wise and logically. Tool keys are stored in secret managers, and third-party plugins operate within whitelists and sandboxes. Observability covers not only latencies and costs, but also flags for leaks, toxicity, and policy triggers. Economics are managed by prompt caches, batching, quotas, and context limits. Risks are handled by appeal procedures, manual review of disputed cases, journaling with pseudonymization, and retention policies. Updates are rolled out via canaries and A/B testing based on real scenarios, with a rollback plan and fixed control prompts. Crucially, change management is key. Reporting on data, versions, prompts, and sources, ensuring any response is traceable back to its configuration and timestamp. Fact 44th. Copyright and AI intersect at three nodes: training, inference, and attribution. Training datasets have historically been assembled from mixed sources, from open licenses to copyrighted fragments. Therefore, the importance of auditing, license marking, and agreements for data access is growing. The issue of inference is more complex. Models tend to overgeneralize, but sometimes memorize rare fragments, a piece of code, or a poem. The risk is reduced by deduplication, filters, and differential privacy. And upon request, checks for matches with reference databases are added. For content provenance, C2PA standards and watermarks are being developed, although their reliability against recoding and reshooting is limited. Legal practices differ by jurisdiction, so conservative engineering, keeping source links, respecting robots and opt-out, fixing data provenance, and providing transparent descriptions of how the system was trained and is used is key. Fact 45th. Interface design for AI determines half of its success. Users need visible railings, a clear indication of capabilities and limitations, a quick action rollback, a check sources button, understandable confidence levels, and tool status. Modes like precise/creative, previewing changes via diffs, editable prompts, and short understatements that the system explicitly asks to clarify instead of confident hallucinations are helpful. For complex tasks, step-by-step progress with named steps and the ability to intervene is crucial. And for automations, an action log and a pre-execution plan. Personal memory is a debated area. It speeds up interaction but requires explicit rules for storage and deletion as well as visual cues when memory is used. Finally, the language of errors. Not "I cannot," but "I haven't found confirmations. I suggest options and sources." This way, the interface teaches the user to work with AI as a disciplined assistant. Fact 46. Data management has become the foundation of any AI system. Without clear rules for origin, quality, and access, a model turns into a black box that cannot be reproduced or protected. The modern tech stack includes lineage, tracking where each document came from and how it was transformed. Data contracts between teams, specifying schemas, update frequencies, allowances for missing data and delays, and monitoring for feature and schema drift so that a sudden change in a field's format or value doesn't skew predictions. Confidentiality is handled before anonymization, removing PII, masking, pseudonymization, retention policies, and provable deletion procedures. Replicability is ensured by corpus versions, dump hashes, and dataset cards with restrictions and licenses. In production, SLA for index freshness, tests for contamination of benchmarks, and canaries, tiny but indicative sets that are sensitive to pipeline breakages, are important. Fact 47. Synthetic data is appealing due to its scale and speed. Generative models, simulators, and domain randomization allowed for populating rare cases, accidents in rain at night, uncommon diagnoses, borderline legal norm formulations. However, synthetic data is two-faced. It easily copies its teacher, reinforcing its errors, and shifts distributions if it's too smooth. A sound approach involves mixes, a real core, synthetic tails, and control groups. Quality is measured on three axes: similarity to reality, fidelity, usefulness for the task, utility, and diversity. Guardians are added: duplicate detectors, checks for private fragment leakage, label validation by external rules. For tabular data, attention is paid to correlations and rare combinations. For text, to factual accuracy and the absence of parasitic patterns. Most importantly, synthetics do not negate ethics. The same prohibitions apply to them as to real personal information. Fact 48. Multilingual AI requires a culture of localization, not just translation. Issues begin at the tokenization stage. Morphologically rich languages and code switching increase length and errors. Proper nouns, place names, legal terms, and social connotations often lose meaning with direct substitution. Fine-tuning on regional corpora helps, but annotator bias and a bias towards major languages still emerge. Tone, politeness, taboos, and acceptable metaphors differ. Practice involves market segmentation, domain adaptation, term dictionaries, and style guides for each language, as well as evaluations with native speakers, and stress tests on dates, currencies, units of measurement, and address formats. Legal nuances are a separate line. Rules for personal data and permissible content vary, so policy and filter control cannot be universalized. They must be locally understood and documented. Fact 49th. For AI, hardware is a race for memory and connectivity. Transformer performance often hits limits not in flops, but in the bandwidth and latency of accessing weights and KV caches. This drives the growth of HBM, interprocessor exchange buses, and fast internode interconnects. 2.5D packaging, chiplets, and specialized matrix units reduce the cost per operation. Sparsity, like 2 to 4 and INT8/INT4 support, are added at the hardware level. In distributed training, 0/FSDP and topologies that minimize all reduce volumes are helpful. For inference, quantization, expert sharding in mixture of experts, and aggressive attention caching are used. At the edge, NPUs in phones and laptops face thermal and battery constraints, requiring compact and energy-efficient modules. The key trend is co-design of algorithms and hardware. Models are designed for available memory and parallelism, while accelerators are tailored for real access patterns. Fact 50. Implementing AI in an organization is a discipline, not a magic button. Teams are assembled based on a role matrix. Product managers define tasks and success metrics. Data engineers and MLOps specialists handle data and pipelines. Researchers focus on models and evaluations. Security and legal departments manage risks and compliance. And the red team conducts attacks and stress tests. At the management level, a change committee is established, a Rossi matrix for decisions is created, and a release calendar with canary deployments and rollback plans is developed. The economics are calculated in advance, covering the cost of data, computing, licenses, support, and staff training, as well as the expected impact, such as process speed, error reduction, and new opportunities. For users, guides, safe interfaces, feedback channels, and appeal procedures are prepared. Transparency is paramount, from model and data cards to action logs and prompt versions, ensuring any response can be traced and, if necessary, challenged. Fact 51. Federated learning enables training models on the edge, on phones, laptops, medical devices, without sending raw data to the cloud. A device performs local gradient steps on its examples, and the server aggregates only weight updates. The classic approach is fed-av. However, reality deviates from the ideal IID scenario. Each client has its own accent, camera, schedule, leading to differing data distributions, while late participants, stragglers, and unstable connections disrupt the round rhythm. Gradient compression and partial client sampling are added to save traffic. Secure aggregation ensures the server doesn't learn the contribution of a specific device. Differential privacy limits leaks through statistics. Personalization addresses the general versus my own trade-off. A shared base plus fine-tuning of a local head layer. Separate concerns include the energy thermal budget and scheduling. Training is initiated at night while charging in small batches. Fact 52. Training with human preferences has become the standard for dialogue models. First, pairs of responses, such as A is better than B, are collected to train a reward model. Then, the base model is fine-tuned using policies like PPO, proximal policy optimization, or simpler procedures where preferences are directly incorporated into response probabilities, DPO. The RLAIF variant replaces humans with a strong judge model, which is cheaper but risks reinforcing its own biases. It's good practice to include human annotations and regularly reevaluate the judges. Importantly, the reward function is fragile. Over-rewarding politeness can lead to a loss of usefulness, and enforcing a style can reduce flexibility. Therefore, multi-aspect criteria, usefulness, plausibility, safety, anti-prompt injection measures, and a refusal policy for dubious requests are introduced. Crucially, there's anti-cheating, logging instances of reward hacking, revising instructions, and periodically refreshing data to prevent the model from memorizing short-term tricks. Fact 53. In cybersecurity, AI acts as both a shield and a potential battering ram. On the defense side, models sift through logs, catching anomalous event sequences, enriching signals with external contexts, and helping analysts write natural language detectors that turn into regex and rules. Generative assistants speed up reverse engineering. They summarize functions, explain network flows, propose hypotheses on adversary TTPs, and code scanners flag insecure patterns. Simultaneously, these same technologies can synthesize phishing texts, variant malware code, or obfuscated prompts. The answer is a perimeter of processes, sandboxes, and limited roles for tools, human in the loop for critical actions, red teams with social attack scenarios, honey tokens and canary artifacts, telemetry on false positives, and retroevaluation. And, of course, a strict ban on automatic execution of malicious scripts without isolation. Fact 54th. Musical models learn not from sheet music, but from sound and symbolism simultaneously. Spectrograms transform audio into pictures for transformers and diffusion models, while MIDI and tokenized scores provide a discrete framework for rhythm and harmony. Control is managed through conventions, genre, tempo, key, chord progressions, and timbre references. On top of these, accompaniment generation, melody continuation, and stylization for an era or ensemble occur. A separate branch involves separating into stems, vocals, drums, bass, noise reduction, and mastering with neurocoders, which bring the mix to a polished sound. The complexity lies in temporal coherence over long segments and subtle sound attack artifacts, causing the recording to breathe unnaturally. Therefore, local windows are combined with global representations of the form. The ethical part emphasizes performer consent and rights to catalogs. Datasets, licenses, and origin markings are as strict as in text and images. Fact 55. The connection between AI and databases goes beyond natural language SQL. To prevent an assistant from making dangerous joins or confusing amount with quantity, it is given the database schema, synonym dictionaries, business field descriptions, and examples of correct queries. Then a strict function calling mode is enabled, where the model only fills in the parameters for functions like select table, join, filter. For security, read-only roles are used, along with limits on the number of rows, time, and cost. A sandbox is provided for subqueries, and DDL, DML operations are blocked by default. On the quality side, a generate, check by plan, explain cycle is employed, where a non-compliant plan, too expensive, unsuitable index, is returned as a signal for correction. Increasingly, vector indexes are used together, enabling hybrid search by meaning and by fields, linking the query to the schema documentation and the data itself. The result is a semantic layer on top of SQL, where a person can see and edit the logic, not just a polished answer. 56th fact. AI standards and management are evolving into an engineering discipline, encompassing not only laws but also practical frameworks. Organizations are establishing model registries that describe their purpose, data sources, quality metrics, and risks. These registries include cards detailing limitations, expected biases, and conditions for safe application. Internal AI committees are being formed, where product, safety, legal, and IT teams align policies, from permissible data sources to incident response procedures. Risk management methodologies are gaining importance, involving the identification of harm scenarios, their probabilities and impacts, mitigation plans, independent validation, and periodic audits. International standards for AI risk management and recommendations from relevant institutions are introducing a common language for defining risks, documenting datasets, and assessing portability. The overarching goal is to make AI operations reproducible, verifiable, and explainable for businesses, regulators, and users. 57th fact. In finance, AI operates at the intersection of speed and control. Algorithms rank loan applications, detect transaction anomalies, predict customer churn, and suggest scenarios to traders. However, every decision undergoes model risk management, independent validation, stress tests, and reports on segment-wise biases. Backtests are built using a sliding window approach to avoid leakage, and strategies are tested for resilience to market regime shifts and black swan events. Explainability is not a luxury. Regulators and clients have the right to know which factors led to a rejection. Local interpreters, calibration reports, and appeal policies are applied. Fraud is combated with graph models and ensembles of time and device features, but limits are placed on automatic blocks to avoid freezing honest customers. In production, there are 3 lines of defense: the developer, independent model validation, and compliance. Above all, journaling is used for investigations. Fact 58. In the creative industries, AI has become a workhorse for pre-production. Generating sketches, storyboards, scene and costume variations, rapid set design from text descriptions, and automatic clean rotoscoping and frame upscaling. Compositing relies on segmentation, and sound on voice synthesis and instrument stylization, which speeds up animatics and pilot videos. However, boundaries are important. Actor likeness and voice are legal rights and require consent. Synthetics must be marked, and training datasets licensed. Practice builds guardrails. Separate environments for draft generation, manual acceptance before release, originality and reference compliance checklists, and maintaining the provenance tree of artifacts. Ultimately, AI does not replace the team but expands its palette, allowing hundreds of safe options to be explored before an artist and director choose one, grounding it with human taste and accountability. 59th fact. In earth sciences, AI assists where data fluctuates across time and space. Neural networks improve nowcasts, short-term precipitation, and thunderstorm predictions from radar. They enhance numerical atmospheric models with rapid local-scale refinements, create flood and landslide risk maps, restore gaps in satellite series, and boost climate field resolution for regional planning. Energy sectors use wind and solar forecasts to balance grids, while transportation optimizes traffic and schedules based on weather. However, physics isn't entirely ceded to statistics. Models are checked for conservation laws and physical constraints, and outputs are cross-referenced with real-time measurements. Risks include recalibration to quiet history and failure during extremes, making stress tests on rare events, ensembles, and conservative uncertainty intervals crucial for responsible decisions. Fact 60. The development horizons of AI are moving towards verifiability and modularity. Schemes are being explored where a language model plans solutions like a program and then executes them with tools, with formal verification of steps. This brings us closer to evidential AI, capable of presenting not only an answer but also the trace of its reasoning. Agentic loops are learning to limit themselves with contracts, explicit goals, permissible actions, budget limits, and strict interfaces. In parallel, the practicality of small, specialized models is growing. These models are fine-tuned with adapters for domain-specific tasks and operate locally, near the data. Large models act as universal task compilers. The role of hybrids combining search plus generation plus tools and content provenance protocols is increasing. Not all of this is yet reliable. Much is in the stage of active experimentation. However, the overall trend is clear. Less magic, more verifiable steps, and controllable decisions. Fact 61. The era of small language models has shown that size doesn't always win. Compact SLMs, weighing hundreds of millions to a couple of billion parameters, with proper data preparation and instruction fine-tuning, can handle entire classes of tasks faster and cheaper than giants. The key is curated domains, tech support, document analysis on a narrow scheme, embedding into offline applications. They are trained on clean corporate corpora, distill examples with step-by-step explanations from large models, and transfer knowledge through adapters. Pros: millisecond latency, on-device privacy, predictable cost. Cons: quality drops sharply outside the domain. Harder to answer rare questions, higher risk of brittle errors without retrieval support. A mature architecture is an SLM as the engine, with indices, functions, and strict JSON output alongside. Fact 62nd. Confidential computing for AI is developing along three lines: Trusted Execution Environments, TEE, Multi-Party Computation, MPC, and Fully Homomorphic Encryption, FHE. In TEE, models and data operate within a secure processor enclave, reducing the risk of leaks even with administrator access. This is fast but requires trust in the hardware. MPC divides a secret among participants with no single party seeing the original values, suitable for collaborative learning in banks or clinics, but with high communication overhead. FHE allows computations on encrypted vectors, a dream for private inference, but currently takes minutes and gigabytes where open-source operations take milliseconds and megabytes. Practice builds hybrids, pre-processing in TEE, splitting sensitive features via MPC, and FHE selectively for the most hot fields. 63rd fact. In agriculture, AI has become a tool for precision farming. Satellite and drone imagery provide plant stress maps. Models classify diseases by leaf spot patterns. And moisture and temperature forecasts help dose irrigation and nitrogen by the cell of the field. Tractors are equipped with visual navigation and weed detection for spot application of herbicides, which saves chemicals and reduces soil load. There are also low-tech victories. Mobile apps recognize pests from photos, returning an action plan to the farmer in minutes. However, limitations are real. Models fail on new varieties and soils. Sensors drift. Shadows and dust spoil images, and telemetry in regions with poor connectivity is delayed. Success is brought by local calibration, seasonal retraining, a digital agronomist as a human in the loop, and transparent economic metrics: yield, water, fuel. Fact 64th. Transferring trained models to a new domain encounters two distinct shifts. Covariate shift, inputs have changed but the label rule remains the same, and label shift, class proportions have shifted. For the former, feature adaptation and unsupervised methods are helpful, such as distribution alignment, moments, contrastive objectives, and test time adaptation, where the model slightly adjusts normalizations directly on incoming data. For the latter, thresholds are corrected and prior probabilities are re-evaluated on unweighted streams. When shifts are numerous and rapid, modularity prevails. A shared encoder plus light domain-specific heads, replay of old scenarios, and canary sets signaling degradation. The myth is that an extra hour of training is enough. Without diagnosing the shift type, one can only reinforce errors. The correct process involves measurement, hypothesizing the mechanism, and a targeted adaptation protocol. Fact 65th. Digital twins turn AI into a testing ground for controlled experiments. Factories, power grids, warehouses, and even individual boilers are equipped with simulations synchronized with real-time sensors. These simulations are used to safely run what-if scenarios, new operating modes, repairs, pricing strategies. The models play two roles. They accelerate physical simulators with surrogates and help fill data gaps. Agent loops explore management policies, considering constraints from temperatures and pressures to delivery SLAs. However, a digital twin is only as good as its calibration. Without regular checks against real measurements and uncertainty assessment, it creates an illusion of control. Practice requires validation protocols, parameter version logging, red buttons for automation, and clear accountability: what the model decides, what it recommends, and where the operator has the final say. Fact 66. Sensor fusion acts as the nervous system for autonomous machines. Cameras provide color and texture. LiDAR offers geometry for meters ahead. And radar detects range and speed in rain and fog. Inertial sensors and odometry maintain pose, while high-definition maps add memory of lanes and traffic lights. Algorithms combine these streams: Kalman and particle filters, factor graphs for simultaneous localization and mapping, SLAM, and priors with uncertainty. At the top level, there's object detection and tracking, prediction of pedestrian and vehicle trajectories, and planning considering dynamics and acceleration limits. The trickiness lies in the tails of the distribution: glare, dirty sensors, reflections, and rare scene configurations. Practice demands a safety case, a catalog of assumptions, degradation plans, speed reduction, manual mode, independent braking channels, logging of every meter traveled, and regular regression tests for nights, snow, and obscured signs. Fact 67th. Clinical language models are changing the routine of medicine in areas where human time is chronically insufficient. They recognize a doctor's speech during appointments, collect medical history, structure patient complaints, highlight red flags, generate draft conclusions and discharge summaries, code diagnoses according to classifiers, and suggest missing tests. In hospitals, they summarize multi-day records and build timelines linking medications, dosages, and reactions. However, they do not make diagnoses. This is the responsibility of the clinical team. Implementation requires de-identification of records, access logs, local domain corpora, department-specific terms, abbreviations, slang, a human in the loop for all therapy proposals, and strict pharmacovigilance frameworks. Effectiveness is measured not by blue and rouge, but by time to discharge, the rate of documentation errors, and readmission rates. Without clinical trials and analysis by sex, age, and comorbidities, no automation is possible. Fact 68. In legal practice, AI functions as a reading and search accelerator. Systems extract entities from contracts, parties, terms, indemnities, IP rights, and compare them against corporate playbooks, highlighting deviations. In e-discovery, models pre-code large volumes of correspondence, surfacing relevant documents and hidden themes. Generators help draft memos or meeting summaries, but each point must be backed by a cited source, case number, paragraph, page. For reliability, RAG is used with closed precedent databases, strict access segregation schemes, and citation chains in responses. Risks include hallucinations and rhetorical conviction by the model, so link verification, prohibition of making up case numbers, and prompt version journaling are implemented. The cultural aspect involves ethics and confidentiality, client secrets, conflicts of interest, data storage and deletion, and monitoring for bias in recommendations if AI influences decisions. 69th fact. At the intersection of AI and optimization research methods, learnable optimization is born. Classic problems like routing, scheduling, and placement are formalized as combinatorics with hard constraints. Alongside them are neural networks that learn to predict good starting solutions, heuristics, or bounds for branching. Differentiable solver layers have emerged. They are included at the end of the model, and gradients flow through the entire task. This allows features to learn what is useful for the final optimal metric, rather than abstract accuracy. This speeds up vendor selection, warehouse titting, power consumption profiling, and material cutting. However, hybrids require discipline. Validation against real-world constraints, shifts, breaks, payload capacity, robust tolerances for noise, estimates for redeployment costs, and clear SLAs. Furthermore, the optimum in simulation is not the same as the optimum in a live system. An A/B loop in production and an emergency stop button for rollback are needed. Fact 70. Artificial intelligence has become an ally in preserving linguistic diversity. For low-resource languages, corpora are collected from radio archives, school notebooks, newspapers, and oral interviews. Texts are aligned by dialects and recording eras, and then speech recognition and translation are trained, taking into account code switching and loanwords. Linguists build morphological analyzers and dictionaries, while models help speed up the transcription and annotation of tones, clicks, and pharyngeal consonants. In practice, community respect and agreement are important. Who owns the data? Whether ritual recordings can be published, and how benefits will be returned. Textbooks, keyboards, local interfaces. Technical challenges include long words, absent spelling standards, and rare proper nouns. These are solved by adapting tokenizers, joint training of related languages, and active learning on complex examples. The risk of averaging is also real. Therefore, dialectal variants are recorded and stored as a value, not noise. Fact 71. AI has become a powerful tool for accessibility. It generates alternative descriptions for images, creates live captions for lectures and meetings, and translates speech to text and back in real time. Assistive keyboards suggest words to users, considering their motor abilities. Multimodal models can read out diagrams and interfaces, recognize objects in frames, and provide step-by-step navigation instructions. For individuals with speech impairments, AI generates phrases using AAC pictograms, selecting appropriate grammar and intonation. Complex tasks involve sign languages, requiring 3D pose annotation for hands and facial expressions, along with robustness to background and clothing variations. On-device models reduce leakage risks, and interfaces adhere to accessibility principles like WCAG, focusing on contrast, focus, and element descriptions. Limitations are evident: hallucinations in descriptions, cultural biases, and network delays. Therefore, user testing with communities and the human-in-the-loop approach for critical scenarios are mandatory. Fact 72. Contact centers are one of the most mature testing grounds for AI. The process begins with speech recognition and diarization, identifying who is speaking, moves to intent detection and entity extraction, then to RAG search across a knowledge base and agent assist, prompts for responses, solution steps, CRM field population, and automatic call summaries. In real time, algorithms suggest the next best action, measure adherence to scripts and compliance, and mask personal data in recordings. Business metrics like AHT, FCR, and CSAT are improving, but not without caveats. Speech accents, background noise, on-code sounds, and language switching can break the models. Hard answers without references harm trust. Practice is a hybrid. AI suggests, the operator approves. Strict JSON output for integrations, white lists of actions, logging, regular evaluations on real calls. Legally important are consent for recording, storage of anonymized data, and appeal procedures if an automatic suggestion was incorrect. Fact 73. In sports, AI analyzes gameplay at speeds unattainable by humans. Optical tracking and sensors on uniforms collect player trajectories, speed, and acceleration. On top of this, load and injury risk metrics are built, along with individual heat maps. In football, expected goals, XG, and assists models are used, while basketball employs expected points models based on defender positioning. Computer vision aids offside lines, automates highlight reel creation, and suggests play patterns to commentators. Coaching staff receives what-if simulations, how pressing will change with a different formation, or what effect a substitution at a specific minute will have. Limitations are fundamental. Data is incomplete, opponent tactics and styles shift models outside their distribution, and overly aggressive risk personalization can discriminate against players. Therefore, decisions are made by people, with AI serving as a tool providing reports on uncertainty and verifiable sources. Fact 74. The fight against deepfakes is a race of signals and disguises. Detectors combine features, lighting and shadow inconsistencies, micro-artifacts from face interpolation, frequency seams after upscaling, mismatches in head pose and glasses distortion. In audio, these are spectral anomalies of formants and breathing, and unstable prosody. Content origin verification is developing in parallel. C2PA signatures and watermarks embedded at the model level and resistant to transcoding. However, there is no 100% protection. Screen recording, printing and shooting, and added noise blur the signals. A realistic strategy is multi-layered. Detectors at platform entry, source and metadata checks, human in the loop for high-profile cases, legal processes for false information, and media literacy training. For vulnerable domains, banks, contact centers, voice anti-spoofing, active calls, and live checks are implemented, combined with a policy of refusal upon doubt. Fact 75. In the realm of cultural heritage, AI has become a magnifying glass and a restorer's brush, but only when wielded by experts. Models segment cracks and varnish layers, isolate later additions on infrared and X-ray images, match pigments with mineral composition catalogs, and reconstruct missing decorative fragments based on period symmetries. Algorithms are used to straighten deformed scrolls, read faded text by enhancing contrast and stylistically reconstructing fonts, and piece together ceramic shards by their edges and patterns. Generation helps propose potential losses for discussion marked as hypotheses rather than truths. Ethics form the foundation. Original works must not be replaced by synthetics. Transparency of all interventions is required. Methodologies must be published, and agreement must be reached with museums and communities. The sole objective is not to rewrite the past, but to carefully reveal its layers, minimizing impact and documenting every restoration step. Fact 76. Open and closed AI ecosystems are not just ideologies, but different modes of risk, speed, and control. Open weights and code provide reproducibility, independent audit, rapid vulnerability patching, and a flourishing ecosystem of plugins and adapters. Licenses determine if fine-tuning and commercialization are allowed and if source attribution is mandatory. Closed models excel in holistic stack optimization and protection against training extraction, but require trust in the vendor and their processes. Corporate practices often involve hybrids, an open runtime, proprietary RAG and indexes, while the large model itself is a managed service with service-level agreements and audit logs. Security depends not only on the license. The supply chain includes datasets, tokenizers, compilers, GPU drivers. Everything is versioned and signed. A balanced choice depends on the tasks. Where transparency and portability are needed, open is chosen. Where SLAs and scale are critical, managed services are preferred. Fact 77. In the public sector, AI is used for heavy, monotonous routine tasks, classifying incoming requests, routing applications, extracting details from scans, summarizing multi-volume cases, automatically calculating benefits, and providing prompts to inspectors during on-site checks. However, the requirements here are stricter than in business: traceability of decisions, explainability of grounds, protection of personal data, and the right to appeal. Technically, this means local corpora in the agency's language, strict ACLs over indexes, access logs, and human-in-the-loop for all actions affecting citizens' rights. The danger is transferring historical biases into algorithms. If regions or groups are underrepresented in training archives, the system will perpetuate injustice. Therefore, independent evaluation by segments, procedures for manual review of disputed cases, and a policy of no automatic rejections without confirmation are introduced. Success is measured not by blue, but by service delivery times, the proportion of corrections, and public trust. Fact 78. In games, AI serves roles from shadow designer to balance judge. Procedural generation creates landscapes, quests, and varied dialogues, while large language models give NPCs voices, memory of encounters, and motivation, making behavior less scripted. Bot testers run millions of simulations, catching economic exploits and level holes. Systems monitor telemetry and adjust difficulty for the player. On the security side, AI catches cheaters by input anomalies and physics mismatches. Risks are clear: toxic content in user prompts, unpredictable responses, server load from long dialogues. Guardrails include filters, topic whitelists, safe templates, local SLMs for millisecond reactions, and strict context limits. AI's creative power shines when it doesn't replace game design, but creates a space of options and believable details that artists and writers select and refine. Fact 79th. In materials and chemistry, AI drives inverse design. Instead of lengthy trial and error, desired properties like strength, thermal conductivity, or absorption bands are first specified. Then, models propose candidates with the best compromise. Generative networks draw molecules and crystal lattices, predictors assess stability and toxicity, synthesis planners create reaction routes, and active learning directs experiments where knowledge gain is maximal. Laboratories are automating. Robots dispense reagents, spectra, and diffractograms immediately feed into a model that updates the hypothesis. Bottlenecks include data fragility, few negative results, publication biases, and the gap between theoretical stability and synthesizability. Therefore, validation cycles of in silico, in vitro, in vivo/in operation are mandatory, along with reproducibility protocols and error reports, so the model learns not only from successes but also from failures. Fact 80. Secure AI-powered software development is like SSDL on steroids. Assistants speed up code generation, but simultaneously expand the risk surface. The engineering process includes policies for AI-generated code, mandatory tests, linters, and typing, checks for licenses and snippet origins, static vulnerability analysis, secret scanners, and a repair loop where a test failure becomes a model prompt. At the supply level, SBOM and artifact signing are introduced, and AI assists in verifying dependencies and searching for supply chain injections. For infrastructure, isolated sandboxes for model execution code, roles with minimal privileges, logging of tool calls, and a ban on network operations without a whitelist are implemented. Culture is as important as technology. This includes prompt guides, examples of blacklisted anti-patterns, regular red team sessions, and success metrics based not on lines of code, but on bug fix speed, incident reduction, and recovery time. Fact 81. Search engines are transforming into answer engines, where a generative model is integrated on top of indexing rather than replacing it. Under the hood, familiar stages are at work: crawling, deduplication, analysis of links and data schemas, schema.org, extraction of passages, and ranking by quality signals. Then RAG kicks in. For a query, fresh paragraphs are retrieved, cited with source attribution, and a language model composes an answer, preserving links and timestamps. The main threats are LLM spam on the web, prompt injections directly on pages, and fact drift. Protection involves trusted domains, penalties for anomalous patterns, citation verification, and sandboxing for tools. Metrics are changing. Instead of measuring clicks, they measure time to the first useful snippet, the proportion of questions with verified sources, and resilience to manipulative websites. For content creators, this is a shift. Structuredness, clear theses, and verifiability win, not volume. Fact 82nd. AI in hiring functions as a structuring and verification pipeline where the stakes are high. Resumes and applications are transformed into entities: skills, experience, domains, certifications. They are matched against competency dictionaries and job requirements. Chatbot assistants suggest interview questions and record answers. However, the legal framework is strict. In several jurisdictions, automating HR decisions is considered a high-risk practice, requiring explainability, bias monitoring, and the right to appeal. Technically, this means transparent features, avoiding proxies for gender, race, or age, calibration reports by segment, regular evaluations on blind datasets, and storage of causal factors for decisions. Good practice includes a human in the loop for every rejection, prohibition of blacklists without verifiable grounds, control over personal data leaks, and retention periods. Companies that aim not for keyword filtering, but for accurate potential identification and fair feedback are the winners. 83rd fact. Power systems are becoming digital organisms where AI aids in balancing generation, the grid, and demand. In grief, wind and solar forecasts feed unit commitment and economic dispatch blocks. Anomaly detection models monitor phases and frequency using PMU data. For flexible demand, demand response policies are built, from smart thermostats to EV charging during cheap windows. Agent-based loops test maintenance schedules to avoid violating the N-1 criterion, and digital twins suggest where network bottlenecks lie. Risks include weather black swans and cyber attacks. Thus, decisions are not put on autopilot. An uncertainty interval is introduced, protection relies on classic relaying, manual control procedures are in place, and a degradation plan is developed. Ultimately, AI does not manage electricity, but proposes verifiable plans that the dispatcher approves based on market rules, safety, and the actual equipment condition. Fact 84th. Biosecurity in the era of generative models requires guardrails at every step so that knowledge helps to heal, not to harm. The correct architecture prevents the output of detailed protocols and dangerous procedures. This is achieved through vocabulary filters, lists of prohibited queries, verification of links to authoritative sources, and, during training, the exclusion of datasets containing sensitive instructions. Red teams involving biologists test models for attempts to bypass prohibitions, and the human-in-the-loop policy ensures that any recommendations are only for professionals and with reference to clinical guidelines. Outside the models, industry practices are in effect: screening orders for synthetic sequences, auditing laboratories, tracking data provenance, and transparency of research objectives. The principle is one: AI is a tool for generalization and search, but not a manual for experiments. Safety and ethics are paramount, even at the cost of refusing answers. Fact 85th. The labor market is changing not overnight nor by professions, but by tasks within roles. AI accelerates routine work, from drafting emails and summaries to initial data and code analysis, freeing up time for client interaction, design, and hypothesis testing. Research shows increased productivity in tasks with a standard structure, but also a risk of pseudo-efficiency, where the number of pages or commits grows while the quality of solutions declines. Therefore, Centaur process designs win. A person sets a goal, AI offers options, and a person checks and makes a decision. Plus outcome metrics, not volume, defects, NPS, closed incidents, cycle speed. Key skills are task setting, working with sources, tool management, and responsibility for the outcome. Employers need retraining programs and a transparent AI usage policy. Employees need the habit of documenting conclusions and the ability to explain where a model might have erred. Fact 86th. In logistics, AI functions as a dispatcher for invisible flows. It forecasts demand for hundreds of SKUs, builds what-if scenarios for promotions and seasonality, optimizes inventory placement across warehouses, and then solves routing problems considering time windows and constraints on weight and temperature. Models listen to truck telemetry, ship AIS signals, traffic data, and weather reports, providing advance warnings about port congestion and overloaded nodes. Internally, there's a whole orchestra: gradient boostings and transformers for forecasts, MILP/CP-SAT and heuristics for planning, graph networks for identifying bottlenecks, and anomalistics for fraud and losses. The risks are real. The bullwhip effect amplifies errors. Distribution shifts break calibration, and rigid on-paper optimization ignores the human factor: shifts, safety, fatigue. Mature stacks add buffers, uncertainty intervals, digital twins of chains, and KPIs not only for SLA, but also for emissions and returns. 87th fact. In mental health, AI is not a therapist, but a supportive layer. Assistants help maintain thought diaries based on CBT principles, offer breathing exercises, remind users to take medication, and track sleep and activity patterns. Language models can gently rephrase catastrophizing and provide reference materials, while risk algorithms detect crisis markers in text and speech, sudden affect changes, mentions of self-harm, long pauses. Important boundaries. Such systems do not diagnose and do not replace a live specialist. They must clearly direct users to licensed services and hotlines in dangerous situations, store data with consent and minimization, and exclude advice outside standardized protocols. Cultural and linguistic nuances are critical. The same word is colored differently in different environments. Reliability is measured not by the beauty of dialogue, but by program retention, symptom reduction on validated scales, and safety. 88th fact. In architecture and construction, AI accelerates the journey from sketch to commissioning. Generative design explores thousands of layouts under constraints such as insulation, evacuation routes, load-bearing structures, and acoustics, offering compromises between area, cost, and comfort. AI-enhanced BIM models detect clashes in engineering systems, predict schedule delays using 4D/5D analysis, and assess the impact of changes on cost estimates. On-site, computer vision from drones and cameras verifies actual progress against the plan, monitors PPE usage, and identifies hazardous zones. Risk models warn of potential material delivery delays. Inside buildings, digital twins and predictive analytics optimize HVAC and lighting, reducing energy consumption. Significant limitations exist. The quality of original drawings, incomplete regulations, unique structural connections, and manual workarounds by contractors. Therefore, decisions ultimately rest with the architect and technical supervision, with AI serving as an advisor providing a clear log of its premises. Fact 89th. In journalism, AI has become both a magnifying glass and a shovel. It sifts through vast arrays of documents, meetings, and budgets, quickly building timelines and connection maps, and aids in OSINT verification, matching shadows and sun azimuth for geolocation, comparing equipment silhouettes, and recognizing tail numbers and emblems. Multimodal models extract key frames and potential editing trails from videos, while synthetic detectors search for deepfake artifacts. The generative aspect is useful for drafts and question sets, but every fact requires a citation and original source. Editorial policies prohibit fabricated quotes and automatic release without verification. Risks include hallucinations and a confident tone that can present an assumption as reality. Protections involve RAG on trusted databases, a citation chain in the text, and a two-stage check, author plus editor. Ethics dictate transparency in AI use and respect for privacy and the presumption of innocence. Fact 90. In laboratories, self-driving scientific circuits are emerging. AI plans experiments, robots dispense reagents, sensors immediately provide spectra and curves, and Bayesian optimization or active learning selects the next step for maximum knowledge gain. This cycle accelerates the search for catalysts, electrode materials, and drug formulations. Surrogate models replace expensive simulations, and digital notebooks record all hypotheses and parameters. But there is no magic. Without negative results and reproducibility checks, circuits learn easy wins. Sensors drift, and a correct maximum in a simulation might turn out to be a dead end in synthesis. Therefore, blind validations on independent setups, uncertainty intervals, protocol pre-registration, and safety red buttons are implemented. The goal is not to replace the scientist, but to extend their hands and eyes, to shorten the hypothesis verification cycle and honestly document the path to discovery. Fact 91. Quantum computing and AI are converging in hybrid schemes, where parts of a task are solved using different languages of physics. Variational quantum algorithms train a small, parameterizable quantum circuit so that its outputs minimize a classical loss function. Parameter optimization occurs on CPUs/GPUs, while the expectations themselves are measured on a quantum device. For machine learning, this manifests in quantum kernels, substituting quantum similarity into SVMs, feature generation, and quantum chemistry modeling with subsequent distillation into classical networks. Limitations are real: noise, a small number of qubits, decoherence, and stochastic readout errors. Therefore, error mitigation, circuit averaging, compilation tailored to device topology, and rigorous benchmarking against strong classical baselines are employed. The nearest practical application is in narrow tasks where physics offers an advantage in feature representation and AI handles experiment control and result processing. Fact 92nd. An AI-powered smart city is a network of interconnected tasks. Adaptive traffic lights reduce queues by predicting traffic flows. Computer vision counts passenger traffic and identifies bottlenecks. And demand models adjust public transport schedules based on events and weather. In utilities, digital twins of buildings forecast heat loss and adjust HVAC by zones, reducing consumption peaks. Routing algorithms optimize waste collection based on container fill sensors. At the security level, AI detects anomalies in infrastructure networks and water leaks. However, the architecture must be ethically centered, minimizing personal data, aggregation and anonymization, prohibiting mass identification without legal grounds, and open reports on metrics and errors. Technical guardrails include verified datasets, stress tests for rare scenarios, resilience to communication loss, and manual operator modes for failures. Fact 93rd. Predictive maintenance turns noise and vibrations into early failure signals. Spectra, envelopes, and statistics over windows are extracted from sensors. These features are then fed into gradient boosting models or temporal transformers, which estimate the remaining useful life, RUL, and failure probability. On turbomachinery and conveyors, the growth of side harmonics, phase skew, and temperature drifts are monitored. In electrical grids, frequency responses and partial discharge spikes are tracked. To build trust, baselines of healthy states, calibration of thresholds for operating modes, and post-repair checks are needed. The model must see recovery. Risks include false alarms, changes in component nomenclature, and sensor degradation. Therefore, signal quality control layers, Bayesian uncertainty intervals, human verification for shutdowns, and an economic cost function for errors are introduced, as sometimes fixing later is more profitable than a false line stoppage. Fact 94th. Astronomy and space operations rely on AI when data volumes hit record highs. Algorithms search for exoplanet transits in light curves, filter out systematic telescope noise, and classify supernovae by photometric features. In radio interferometry, networks solve inverse problems for image reconstruction, and on satellite imagery, vision systems assess forest fires, ice melt, and urbanization dynamics. For space traffic, AI helps track objects via radar and optical trajectories, merging observations from different sources and estimating collision probabilities. Planners optimize maneuvers for fuel efficiency and communication constraints. It is critical to consider false positives and incomplete object catalogs. Decisions undergo verification by astronomers and controllers, and models are equipped with confidence scales and reproducible metadata, from calibrations to pipeline versions. Fact 95th. Personal knowledge and AI converge in a second brain, where embeddings, retrieval, and generation build a living layer over notes and documents. Notes are broken into chunks, indexed vectorially, and a conversational model responds with quotes and links, connecting notes by topic and date. Useful features include auto-summaries of meetings, extracting tasks into checklists, generating tables of contents, and creating concept maps with who, what, when transitions. Risks involve false memories due to inaccurate links, leaks during cloud synchronization, and the mixing of private and public corpora. Practices include local indexes, encryption, explicit sources in every answer, note versions, and a changelog. To avoid drowning in automation, rituals are introduced. Weekly reviews, manual tags for key ideas, and archiving outdated material. AI here acts as an editor and navigator, but the final responsibility for the structure and meaning of personal knowledge remains with the owner. Fact 96th. At the intersection of AI and neurointerfaces, there is vigorous work underway to decode intentions directly from brain activity. Electrocorticography and single neuron recordings provide dense signals for controlling prosthetic hands. Models recognize spike patterns, learning grasp, rotation, and force. In the non-invasive variant, EEG/MEG, accuracy is lower, but sufficient for a cursor, selecting letters via a matrix, and basic communication for individuals with locked-in syndrome. The network is trained during calibration sessions, accounting for electrode drift and fatigue, and then a feedback loop is closed, visual or tactile, so the user grows with the device. Experimental systems already translate imagined speech into text, and visual prosthetics encode scene contours into stimuli. Limitations are strict: individual variability, data sterility, ethics, and thought privacy. Therefore, neuro-AI is positioned as an assistive technology under specialist supervision. Fact 97th. Swarms of robots and drones require real-time coordination by AI. Dozens of units must scout, transport, collect, and avoid collisions. Control is built in layers. Local avoidance rules, potential force fields, barrier functions are combined with global graph-based planning and task assignment via matching. Multi-agent reinforcement learning trains joint policies, from role distribution to passing a goal relay to the nearest unit. Communication is unreliable, and sensor dropouts are inevitable, so architectures are robust to delays and packet losses and protocols to leader failure. Safety is not optional. Geofences, altitude corridors, backup parachutes, strict speed limits near people, manual override. Transferring from simulation to physics requires domain randomization, wind, lighting, IMU noise. Applications include warehouse inventory, power line inspections, search and delivery, but every flight is under rules and with a telemetry log. Fact 98. In telecommunications, AI is becoming the autopilot for the radio network. It predicts traffic by hours and quarters, on-the-fly adjusts slot schedules and modulations, and manages the beams of massive MIMO, adapting the diagrams to moving clusters of subscribers. In RAN, self-configuring functions are being implemented. Automatic selection of cell parameters, compensation for overlaps, and detection of silent interference. At the transport level, models identify anomalies in delays and packet loss, suggesting reroutings. At the edge, AI distributes resources among AR/VR streams, games, and industrial IoT, adhering to SLAs for different network slices. A network digital twin is also emerging, a simulator where AI tests policies before enabling them live. The bottlenecks are portability between cities and vendors, fairness among subscribers at cell borders, and compliance with protocol standards. Therefore, solutions undergo sandbox testing, canary deployments, and engineer oversight. Fact 99th. Verifiable AI is a new branch where not only accuracy but also cryptographic proof of step correctness is important. ZKML attempts to package inference into a short proof, snark-stark, so that a third party can verify. A model with hashed weights indeed produced a certain answer for a given input without revealing the weights themselves. This is useful for outsourcing computations and for model marketplaces, but is currently costly in terms of time and memory. Therefore, hybrids are used: Trusted Execution Environment, TEE, attestation, signatures on weight and tokenizer versions, and cache integrity checks. In parallel, watermarking on weights and outputs, provenance cards, and training logs that record datasets and operations are being developed. The idea is singular. Answers should be not only plausible but also verifiable, via hashes, signatures, schemes, and computation traces, with a clear trade-off between privacy, speed, and cost. Fact 101. The most challenging AI tasks remain open. Reliable multi-step reasoning without confidence errors. Long horizon planning considering constraints and information cost. grounding knowledge in physical experience and causality over correlations. Models lack stable memory without forgetting and generalization abilities beyond training distributions. Safety hinges on robustness to attacks and honest uncertainty estimation. Evaluation is also a challenge. Benchmarks age, leaks, and test overfitting distort the picture. And real-world metrics, cost, latency, verifiable link share, human impact, demand observability discipline. Therefore, the course is clear. Less magic, more tools, logs, verifiable steps, and human oversight where the cost of error is high. AI is growing as an engineering system, with frameworks, protocols, and accountability.